next presenter, Dr. Asmaa Adel Rashidi. Dr. Rashidi is lecturer at the Faculty of Engineering, Port Said University. Dr. Asmaa presents an article titled Innovative Nano-MOF-Based Polystyrene Nanofiberous Hybrid Membrane for Groundwater Desalination.
Session today. I'm presenting today a paper entitled Nano-MOF-Based Polystyrene Nanofiberous Hybrid Membrane for Groundwater Desalination. The outline for the presentation of today is introduction to the present work, then the experimental work and the relevant discussion, followed by conclusion, the future work, and recommendations. As discussed before from our colleagues, water shortage crisis is becoming more alarming concern globally. According to the United Nations report in 2021, by the year 2040, a water stress problem will be faced in 40% of the world population, and other reports also estimated that by the year 2025, more than 70% of the world population will have limited access to sanitized and fresh water. So regarding the situation in Egypt, alarming reports have shown that Egypt has already entered the water poverty phase and is dramatically heading to absolute water scarcity with 500 cubic meters per year per capita, while the world average is 1,000 cubic meters per year per capita. Therefore, the need for fresh water resources such as seawater and groundwater desalination have gained considerable attention during the last decade. On the other hand, membrane technologies have proved their superiority over other conventional desalination techniques, as they are more energy efficient and cost effective. In particular, membrane distillation systems have proved to be competitive with traditional desalination systems. So what is membrane distillation? Membrane distillation is a thermally driven membrane-based technique where a microporous membrane separates two aqueous solutions at different temperature. The driving force here for the process is the partial vapor pressure difference at the both sides of the membrane, which is originally generated by a temperature difference on both sides of the membrane. This video here illustrates the operation of the MED process. Sorry. Membrane distillation configurations are divided into four main categories, which are the direct contact membrane distillation, where the feed channel and the permeated channel are in direct contact with the membrane surfaces at all times, and the air gap membrane distillation technique, where a cooling surface is mounted at the permeate side, where the vapors transmitted from the feed channel are condensed here and collected to be condensed. The vacuum membrane distillation technique utilizes a vacuum pump at the permeate side to drag all the vapors that are transferred to the permeate channel and convey them to an outsider condenser to be collected and condensed, which is outside the membrane module. The sweeping gas membrane distillation here, it utilizes a sweeping inert gas at the permeate side to sweep all the vapors that are transferred to the permeate side. Our work is focused on the direct contact membrane distillation technique, as can be shown here in this figure. So what are the advantages of membrane distillation? Over conventional thermal distillation processes such as the MSF and MED, it has smaller footprint, lower operating temperature, which is around 50 to 80 degrees Celsius maximum. The feed can be heated by waste heat or renewable energy sources, and also it has many advantages over the other pressure-driven membrane processes, which is such as RO. It has a lower operating pressure. Usually, MED operates at atmospheric pressure. Its ability to treat streams with high concentrations, its low essential mechanical properties, and the rejection efficiency theoretically can be approximately 100% for the non-volatile components. The limitations of MED, which is despite the wide merits of MED over other desalination techniques, that it has the flux decay phenomenon, the uncertain energetic and economic costs, the very high cost of the required membranes with the required characteristics for successful MED process, and the membrane poor wetting phenomenon. My research is concentrated on the high cost and the poor wetting phenomena. So what is the wetting phenomena, or what is the poor wetting phenomenon? The wetting phenomenon happens when the transmembrane pressure exceeds the liquid entry pressure of the membrane. So the feed water here bridges to the other side of the permeate side, so the permeate flux decline happens, and the depreciation of water quality is considered. So the experimental work here is mainly divided into optimizing the electrospinning conditions and the synthesis of ZIF8 nanofiller and its characterization, and the compositing of ZIF8 with a polystyrene membrane, evaluation of anti-wetting properties, and studying the performance of the fabricated membrane. These are the investigated filler loads, and the characterization used in these studies are listed here. This is an actual photo of the system used, and this is the membrane cell constituents, which is the feed channel, permeate channel, and fabricated membrane. These are the conditions that we studied for the DCMD operating conditions. First of all, preparation of polystyrene membrane from the 12% concentration solution yielded a heavily beaded structure, as can be seen here in this stem image, while preparing a polystyrene nanofibrous membrane from polystyrene 15% yielded beadless continuous uniform fibers, but it has a very big mean fiber diameters. So a salt was added to the polystyrene 12 solution to lower the mean fiber diameter of the reduced membrane. But lowering this mean fiber diameter decreased the contact angle considerably. So to address this problem, we synthesized the ZIF8 hydrophobic nanofiller. The ZIF8 nanofiller was successfully prepared, as can be seen here from the SEM and TEM images. The typical rhombic dodecahedral morphology of ZIF8 can be clearly seen from these SEM and TEM images, and the IR and XRD studies also confirmed the successful preparation of that nanofiller. The PET results also gave that the ZIF8 possessed around 1,200 meters square per gram PET surface area, and it was proved to be stable up till 359.28 degrees Celsius, where it experiences a 15% weight loss. The investigation of the optimum filler loading was carried out. It can be seen here that increasing the filler load to 2% yielded a membrane with a static water contact angle of 150. The 3D laser imaging also proved that the higher surface roughness of the membrane, which proved the super hydrophobic character of the composite membrane. Okay, the performance of the DCMD cell, we can see here at the effect of the feed inlet temperature increasing. The feed inlet temperature increased the permeate flux considerably. Also, we can see here that the composite membrane has a higher performance than the neat polystyrene membrane. Also increasing the feed inlet temperature increased the permeate flux considerably due to the turbulence promotion. Increasing the feed inlet concentration, which is the salt concentration, decreased the permeate flux due to decreasing the vapor pressure difference, which is the main driving force of the operation. Also, the membranes fabricated was studied for extended hours of 8 hours, and it was found that the composite membrane exhibited the most consistent performance rather than the neat polystyrene membrane. So, in conclusion, the ZIF8 nanoparticles were successfully synthesized and incorporated in the polystyrene membrane. It approximately increased the water contact angle considerably to 159, and also it increased the permeate water flux by approximately 50%. The salt rejection values of the composite polystyrene ZIF8 composite membrane combined with its high permeate flux and the fact that it is produced from a cheap material make it an excellent candidate to be used in groundwater desalination via MD applications instead of other commercially available techniques.
Thank you very much, Dr. Asmaa.